So good morning, everyone. I'm Rafael. I work at Intel, but mostly I work on the Linux kernel. I'm a Linux code kernel code maintainer. For those who don't know me, I started to contribute to the Linux kernel in 2005, and then I have been maintaining different pieces of the kernel code since 2009, and the majority of them are related to power management, which is why I am here. So interestingly enough, my first Linux conference was a kernel summit in Cambridge in 2007. So yes, I've been here. I was here almost 20 years ago, and it looked different. So interesting experience. All right, so I live in Poland, near Warsaw, in one of the satellite cities of Warsaw, kind of in a like suburb neighborhood. So the left hand side photo is my backyard, and this is a visitor my house. So okay, yeah. So today I'm going to talk about CPU idle time management, which is almost all about doing nothing efficiently. So if a CPU doesn't have a work to do, which means doesn't have any tasks to run, it is idle, and then it is good to reconfigure a processor or an SoC to reduce power and save energy this way. So every time the CPU is idle, we want to do that. Fortunately, there is support in hardware and in platforms for this. So generally speaking, processors or SoCs have low power states that can be used to reduce power if CPUs are idle or have no tasks to run, and that is done by in a majority of cases, that is done by entering a mode in which a CPU doesn't execute instructions, and that allows things to happen, because if it doesn't execute instructions, then you can say gate a clock to it, or power gate it, or do other more complicated stuff. So in support of that, there are so-called idle states, which essentially represent opportunity. So every time the CPU is idle, is an opportunity to reduce power or save energy. And idle states represent different things that can be done when it happens. And they are per CPU, because it all starts with a given CPU becoming idle, and there's a piece of information that's on the input, right? This CPU is now idle, and now you can do something to reduce power of the whole chip. So for this purpose, there is this piece of code called the idle loop in the kernel. That it roughly follows the diagram in the slide. It is more complicated. There are details that are not covered by it. There are corner cases that are not covered by it, so it's just a rough approximation of what happens. So basically, when a CPU doesn't have any tasks to run, the scheduler no, not visible. Okay, sorry. So let me use my hand. Then the scheduler goes to this part of the code, which is the idle loop. Every iteration of it is the selection of an idle state
Rafael, does the mouse work or does it work? No. I mean, the mouse on the laptop, does that work?
Mouse on the laptop, maybe yes. Let me try. Oh yeah, that works actually.
So that way the video and everything gets it as well.
Yep. Okay, so that's the idle loop, and as you can see, it manages two things. So first of all, it selects the idle state to use for that time. And then it also manages the scheduler tick, which can be either stopped or retained depending on what idle state has been selected. So, yeah. So idle states are basically each idle state is a couple of two numbers. One of them is an exit latency, which is about how much time it takes to reconfigure the processor of the SoC to reduce power. And there are two phases of it. So there's an entry phase and the exit phase. Oh, by the way, I should probably go back to the previous slide. Sorry about that. One piece of terminology. So after selecting the state, the processor is reconfigured to actually reduce power, and this is referred to as entering that state. But actually, this is basically about changing the configuration of hardware. That's to be precise, right? So there are two parts of the exit latency. There is an entry part and exit part. And the entry part is the part when the hardware is configured to reduce power, and the exit part is obviously the part when the hardware is configured to start working again, so that the CPU can execute instructions again. So this is one parameter, and the other is the target residency, which is the minimum time to stay in that state, or minimum time to spend after entering it, so that any energy is saved. Because if it's if the target residency is not is missed, then an attempt to enter the state is actually a waste of energy. It's not a gain. Okay, so there are two things. The exit latency is supposed to be the worst case exit latency, because if there is a latency limit set for CPU idle time management, that limit cannot be violated. So that is supposed to be the worst case exit latency, and there are certain implications of that, let us say. All right. And the piece of code I'm going to talk about going forward is the governor, which is the part selecting the idle state to use in every iteration of the idle loop. And from its perspective, the idle states are organized like those tools in the slide. So they are ordered by the exit latency and the target residency. They are ordered by the time. So the higher the exit latency, then the more energy can be saved in principle by using that state. And that therefore the states on the right-hand side are referred to as deep states, which means that more energy can be saved by using them, and the ones on the left-hand side are shallow, which means that they allow to save small amounts of energy relative to the working state, or the state in which the CPU executes instructions. So the governor sees an array of idle states per CPU, and again, this is per CPU because this is how, from the scheduler perspective, the CPUs are individual entities. So when one CPU becomes idle, then this is all about this particular CPU. Of course, there are dependencies in hardware and there are dependencies in software, but all that is critical from performance perspective, at least for some workloads. So it does, the selection of the idle state, entering it, and so on needs to happen quickly. And that's why the dependencies are mostly not taken into account, at least in the cases when shallow idle states are used. When deep idle states are used, there is some more time to do more deliberate things, and then dependencies can be taken into account. All right, so we have this array of idle states. Now the governor has to decide which one to use, or which one to pick. Okay, there are a few known problems about this or with that. The first one is related to the exit latency and the fact that it is supposed to be the worst case exit latency, because it is generally hard to measure the worst case number, right? Because you never know if you have experienced it already. Maybe yes, maybe not. So this is always an approximation, and the approximation is, using the assumption that if a measurement is repeated for a sufficiently large number of times, then, from the statistics perspective, chances are that we will experience the worst case. Okay. Now there is another problem related to the exit latency, which means that in order to select an idle state like a suitable idle state, let's just say, the governor needs to measure the duration of the idle period every time after exiting the idle state, because then it can build up some statistics and use those statistics to carry out the selection next time. So the idle time needs to be measured. Okay, but the problem is that there is this exit latency. So yes, we can measure the time between the point when the idle state is entered and the point when it is exited, because those are 2 points when the code runs on the CPU, right? So we can, snapshot the other one and the other and measure the time between them, but that's not the idle duration, because this includes the exit latency. And because the number we know is the worst case exit latency, this is not the exit latency that's included in that number, because the exit latency is most of the time shorter than the worst case. I would say it's almost never the worst case. So the way that the governors deal with it is to actually take half of the worst case exit latency and use it as an approximate of the average, which is a problem because it's not accurate in any way, right? So one of the possible improvements of all of that might be to actually add the average exit latency to as an additional parameter and use it in computation, maybe. Right, the same problem happens when in the previous slide there was a case when the CPU actually spent some time in the idle state. But in this case, it doesn't spend any time in the idle state at all. However, the exit latency still applies, because there is a point of no return in the entry and exit procedure. And if you go after the point of no return, and you have to do the whole entry and then exit, and that's the latency you will experience. Obviously, no energy is saved at all in this case. And again, the whole idle duration in this case is the exit latency, in fact. And it, again, is taken into account in the same way as before. One complication on top of all that is, as I said, we have a idle states per CPU, an array of idle states per CPU, which doesn't take dependencies into account and doesn't take hierarchies into account. And the modern chips are hierarchical by nature, I would say. So there is a hierarchy of different units in an SoC or CPU or a processor. Sorry, when I say CPU, I mean a logical CPU in the from the kernel perspective. So a CPU can be an SMT thread or a core or one thread. The processor is a collection of those. It may be a number of CPUs. So there is a hierarchy in a processor which can influence or I would say that the idle states are defined in a way that takes this hierarchy into account to some extent. But because the table of idle states or array of idle states is one-dimensional and per CPU, the hierarchy obviously cannot be entirely taken into account. This is an example of an Intel chip which has 2 hyperthreads or 2 SMT threads per core, and there are 4 cores in a processor. And there are like 4 levels of hierarchy. So the first level is the core level, then there is the CPU level, then the core level. Then there is a package level, and the package is represented by this blue rectangle here. And there is a core. So okay, sorry, three levels, and there is an SoC level which also covers the package and some other things in addition to it. So on Intel CPUs, the way to enter an idle state is to execute the mwait instruction. mwait instruction says, okay, now the CPU is going to be idle and it doesn't need to execute instructions anymore until it is woken up. And it has one parameter, which is a hint, and a hint represents the predicted duration and latency tolerance for the idle state to use. Each of those hints, those hints are numbers, and for every processor there is a different set of hints that can be used. But they are for humans to, or for yeah, for humans to manage all of that like more easily. There are labels that are attached to those numbers, to those hint numbers, and they are like for Intel CPUs, they start with the letter C, and there is a number which corresponds to the depth of the state. The larger the number, the deeper the state. But this is from a single CPU perspective. So when there is only one letter before the number, this means the core level. When there are 2 letters, this may be the CPU level, sorry. When there are 2 letters, that this is a core level or a package level. And the numbers go from 1 to 10. Easy, they are never larger than 10. And this hint gives the processor a license to do something in order to reduce power. It's like saying the processor, okay, the CPU is not needed, it will not execute instructions, and you may do something to reduce power. And the number after the C letter tells the processor how far it can go with that. So 10 means go as far as you want. You can do anything. 1 means do as little as you can. everything between the 10 and 1 is different levels of this license. And so, for example, 6 means that, okay, you can power gate the core, but also you can power gate the package.
Okay, to take a quick question. Yeah, so from the perspective of the OS trying to model the hardware for every single different chip you're going to have, it sounds like you need to build really a separate model of the latency for each of these 10 power levels. Is that correct? Because you're going to have different latency characteristics when you deep sleep at level 10.
Yeah, exactly. So those, yeah, I'm getting to that.
Yeah, but the question was really more of a previous slide, is that, you know, whenever we in the OS or other system software are trying to model the hardware, it's been a million years since I had an intro stats class, but it just seems like we should be doing things from first principles correctly vis-a-vis statistics, that like rather than making this assumption that half of the observed maximum is the average, we should be building a little model of the distribution. And then when you're doing something like, well, you can either directly calculate the average, or you can estimate for some number of nines what an upper bound would be. Is there some reason we don't use more statistics in either online in the kernel or for sort of offline pre-characterization of different?
So there are only 2 parameters per idle state. That's a consequence of the development of this code. So it was decided that there will be 2 at one point. And I already made a comment that it could be improved by adding the average exit latency as a 3rd parameter for each idle state.
Why do you feed it in as a parameter rather than just being observing the distribution and trying to model the hardware derivative?
Because we can't measure it from the kernel.
It can or cannot measure?
Cannot measure it.
Oh, I see. I missed that. I thought the kernel could always. I thought you could always.
If you look at this slide,
issue in-wait instructions to kind of benchmark it.
No. So the what we can measure is the duration between the last instruction executed on the CPU and the first instruction executed after wake up, right?
Yeah. So
which includes the exit latency, but it also includes some other time, and you can't tell the difference between the two essentially. So the exit latency needs to be an external parameter to this.
I see. It's because you can't directly observe that shorter time.
Okay. So in fact, what happens is we do measure that. So we run some measurements and do measure those exit latencies, but because we have only 2 parameters for each idle state, and then we are limited by this basically, and we use the worst case exit latency because that's needed when the limit is set.
So, okay, if I replay, what you're saying is, if you had an average exit latency parameter, that would be directly useful to you in the idle governance.
Yeah. And specifically, actually, in this, when I measure this thing here, if you look at the screen, if I measure this thing here, I could then adjust it by subtracting the average exit latency from it, and then I will have a number that is more likely to represent the real idle duration.
What would be even better if at every wake up you got a number from either firmware or the hardware to say, for this wake up, this was actually, I know it's not easy, but like in theory that would be.
Yeah, but actually it's sufficient to have an average, because it will average out anyway after a sufficient number of repetitions, right? So it's like average is fine. Well, statistically. But it could, yeah, in theory, it could be better. I actually don't know if it will improve anything. I haven't tried it because I don't know those numbers, but.
I didn't see much, but because I disagree with the statistic argument, because, for example, you don't measure, you don't model cluster, for example. So you keep subtracting exit latencies that aren't possible even in theory. So actually, you know, depending on how that is for your particular workload, how often the cluster sleep is actually possible, like your statistical argument of the average doesn't hold, in my opinion, as strong, but yeah.
Or like what kind of average? It's the moving average?
Well, no, just the average.
Yeah, but
Because in the
moving average.
this is not the moving average, just the average.
Just
because yeah, just the average. Because then you can argue that if you repeat the same exercise for 1,000 times, then on the average,
Yeah.
you get the right result, right? But yeah, again, this is like kind of hand wavy. I agree that. So let's get back to this. So there is this hierarchy. The C number tells the processor how far it can get, and obviously the X latency that we put into the idle states table must reflect the worst case X latency that can happen, and so it. Or as a result for C6, it has to reflect the X latency to enter the package C6 idle state for the whole package, which is much longer than the X latency for the core, which will be core C6 X latency. So, and the important part is that when you put a C6 hint into to the M8 instruction, or you pass the C6 hint to the M8 instruction, it actually means the license to first enter the core C6 at the core level and the package C6 at the package level at the same time, conditional on various other things, right? So if all of the other cores in the package are also in C6 or deeper, then you can go into PC6. But if those cores are not in C6 or deeper, then you can only enter C6 at the core level. And that is all like kind of hidden in that idle states table because we only have one X latency number, and it must be the X latency for the package level. There is no way to say anything about the core level X latency, which is what you are talking about, as far as I understand. And the other thing is that the target residency. So which target residency to use in this case, for the core or for the package? And that is not an easy problem to solve. So people use different numbers there, and okay, there is a problem with, or there are problems with this hierarchy, and this is an example of those problems, where you can actually miss a target residency for PC6 if say one core enters the core C6 idle state, into the package idle state, but the other core is idle initially, and then it enters the core state, the C6 core state, and again it has the time to go to the package state, but then a wake up happens on the first CPU, and as a result, the package doesn't stay in a package state for enough time, and that's one of the problems. There are other problems you can easily find in that are related to the hierarchy.
Rafael, in your case, each core requests for a state independent.
Yeah, that's a feature. Yeah, so that's the remark are made in the beginning. So this all happens. So from the idle loop runs on a specific CPU. So all decisions are made with this CPU.
For some platform, at least on ARM, we are using the OS initiated, because at the end, when the last CPU enters CC6, then it can see when the next CPU in the package will wake up and decide to enter the PC6 or an idle one. Even if the first one wanted, there is no way to do that in Intel. You don't know.
No, because all that is decided by firmware. In some cases, you can avoid those things if you put some logic into the kernel for the management of the hierarchical states, which is done, of course. But for Intel, it's not the case, and So, but this is just an example of what can happen, what kind of problems can arise. All right, so in 2009, when I was last talking about that in this conference, there was kind of a rule of thumb, which was that, okay, if you select an idle state that is too shallow, it hurts energy efficiency, because obviously you could save some more energy by using a deeper idle state. Well, if you select an idle state that is too deep, then it hurts energy efficiency and performance at the same time, because then there is too much latency, and you would be better off by using a shallower idle state. But the hierarchical issues, or the issues related to hierarchy, mostly affected deep idle state. All right, that was in 2009. So fast forward to 2005. Okay, so this is a photo taken in 2009. Some construction in Warsaw. This is the same place in 2005. So it changed a bit. And from the governor, idle governor perspective, it's also changed since 2009 to 2005. And that's because of something that happened in the late 2004. So we had this kind of battlefield situation when somebody made a kernel change that reduced the overhead. And I said significantly, but it actually means by 80% or something like that in some use cases. So as a result of that, the kernel spent more time on computing stuff, or less time, sorry, on computing stuff, and more CPU idle time became available in some cases. Okay, so the menu governor decided, oh, I have more, yeah?
To be precise, kernel overhead for doing what?
I don't remember exactly. This was for related to, I believe, software argues or something like that. So something unrelated to running threads, actually, just pure kernel overhead. Or RCU or similar. I don't remember exactly what that improvement was, where the improvement was, but the net result was that CPUs could spend, more time in idle as overall. So it looked to the governor, then it could use deeper idle states more often. And it started to use deeper idle states more often, and then some benchmarks, the performance of some benchmarks degraded because of the exit latency. We did some investigation, and it turned out that the menu governor actually falls back to the deepest available idle state when it cannot select anything else. It has this kind of logic. So, which may not look like the, super good idea, because it's very conservative, right? So an attempt was made to change the behavior, but it introduced a regression on some systems, and interestingly enough, it was not a power regression, but it was a performance regression, which was totally unexpected at that point. Because I could understand the power regression, right? Because instead of, asking for deepest idle state every time when we cannot make a high confidence prediction, we will just use a shallower one, so we use more power, and then, or more energy, I should say, And yeah, and so I can understand an energy efficiency or power regression, but the performance regression was a surprise. And most likely the problem is, I'm not actually exactly sure what happened, but most likely the problem is that if the system is thermally constrained or power constrained, then there is a power limit and there is a power budget. And the more idle states you use, or the deeper idle states you use, the more energy you have for other things, especially for ramping up the CPU frequency in some cases. So if you run single thread stuff or workloads, then actually using deep idle states is good, because then you have more power for running things faster on this single core or single CPU. So we had to revert the change. So, okay, so this is an illustration of,
Oh,
yeah,
a while ago, you also wrote that TOE
yep,
governor.
yep.
Why are people still using menu?
It's the default.
Yeah, well, but that's not the only.
Can we change?
No. That's not the only reason. So they actually are different. So this behavior is important here, because the tail governor doesn't do this, and people actually want this in some cases, as it turns out. So if you switch from one to another, then people see regressions in performance. Surprisingly enough. That's why I'm, that's the reason for this talk today, because it's not that simple, as it turns out. I wish it would be that simple. Right. So making improvements can be hard, as seen in this photo. So this is a railway station in Warsaw that was being reconstructed while in use, sort of, which took like several years to do. Unfortunately, it's completed by now, but the photo was taken when this all reconstruction was underway. Okay, and we have a new rule of thumb which needs to be extended to cover this power limit or power budget case, and which makes governor development a bit harder, because now you have to take all of this. You have to take this possible dependency on the power budget into account. It doesn't change things a lot, but it actually means that you have to bet that if you want the governor to be perfect, then it has to make perfect decisions every time, which means that it always has to predict an idle state that matches exactly the following idle duration, and
Good luck with
that's hard.
But it's not just hard, it's also you would still see that regression, because, like, correct me if I'm wrong, but in that case, the patch actually made much better decisions in terms of the metrics.
Yeah.
It is just that these higher P states on the other cores.
Right. So on paper, by the metrics, it was actually an improvement.
Yes, but because we are.
But by the measurements in the real world, it wasn't. So, and that's really a depressing thing. So,
because we are completely per CPU, I still think this is a massive improvement, but maybe we need to, extend the architecture in the sense a little that, let's say, the governor.
Hold this thought, okay? So we'll get to that in a while. So okay, so from the what the criteria for success are really. What does it mean to be successful? So this is actually an example of some controversy. So the white buildings in the middle are parts of a historic factory that was located in this area, and it actually is there still. But the large building was built on top of it. So it's like covered by this new construction, but it's kind of incorporated or embedded in its ground floor. So if you enter this building, you can actually see some old buildings, like how they look like from the inside, but you cannot see them from the outside. And so this was done because this factory was occupying a very attractive area in the middle of the city. So somebody decided that it can be recultivated or reused by doing something, and they decided to build this whole structure on top of it. But the question is it successful or not? Like, how you measure success in this case? Commercially, it was successful, right? Because it was the otherwise unused land was put to use. But from the conservation principle, maybe it was not a success. So it's hard to say. And again, we have this problem with cpuidle governor development, because first of all, I think that we need to reconsider what success is, and then figure out how to measure it somehow. I don't really have a recipe for it today, unfortunately, because I don't know how to define it, how to define the criteria for success, right? For this case, would it be running some workloads? Would it be, if so, then what workloads actually? Is there a set of workloads that can be used as a canonical set of workloads or something like that? This is like, we can continue the thing that you started 2 slides ago. Like,
okay, so for me, the key insight here is choosing the deeper state, or actually choosing the accurate state, which was the regression, like the better state. Success here depends now on if another core wants to use a higher P state that is unlocked by the fact that we go deeper here, right? Because it would be silly to go deeper, which is an idle miss, if no other CPUs wants to use one of those unlocked P states, right? That would be wrong. Objectively, it would be a power regression as well. So to me, it doesn't seem sensible that the CPU idle governor would care about P states of other CPUs. So why doesn't, for example, another part of the kernel, into P state, Sugov, whoever who knows about another core wants to use an power budgeted P state, say, okay, that's nice that you wanted this idle state, but your latency tolerance says I can upgrade you to a way deeper one, and I will do that. And at wake up, the idle governor gets the information, oh, actually, you've been upgraded by Intel P state to a much deeper state, because Intel P state thought.
Yeah, so that can also be done in the firmware.
It can be done in the firmware, yeah.
The problem with this is that we would essentially, in a context of the example here, it would mean we always would need to ask for C10, because that allows because if we asking for a shallower state,
yes,
limits the choice, right, in this case. So
the problem I see is really that the hint is both mangled into one. It really should be, this is the absolute, like, this is the maximum latency I'm willing to tolerate at wake up, and this is my estimate of what this idle residency is going to be like. And then the firmware or other parts of the kernel are free to upgrade within my minimum wake up latency tolerance that I've specified. So I think these are really like two different values, and there should be something coming from the firmware or other parts of the kernel to say, by the way,
ideally,
this is what you've requested. Fine.
Yeah, so I generally agree. I generally agree, but the question for now is what to do in the absence of that of all that.
I mean, absence of
firmware. Yeah, the firmware works the way it does. It's like also the cpuidle drivers work the way they do.
Yeah.
It's not much we can do.
Right.
So to me, the key point here is basically that there is this power limit or this power budget that, and if it's there, then cpuidle needs to work differently than without it, because then it kind of changes the rules upon us, sort of, right?
So for the core level power reduction, do we actually need the very deepest idle state like menu does, or is biasing towards a slightly deeper state sufficient?
So depends. Sorry for switching back and forth, but in this particular, actually in this example, there is C7, which I didn't mention, but in some cases, the only way to actually unlock C7 is to ask for C10. And if your C7 is necessary at the core level to unlock, enough of a power budget to do something else, then the only way to ask for it is to ask for C10.
I hate computers.
I mean, it seems like the solution here is to fix the firmware / algorithmic pieces that run deeper in hardware, rather than try to rework it or patch around it in the kernel, which would be terribly hard because that is not scalable, and then you would probably end up fixing it a few generations down the line anyway.
Yeah.
But yeah, fixing it in firmware and hardware is not trivial either, because these people have ideas too.
Well, it's a different problem. It's not a technical problem.
I didn't quite get what your argument is against letting Intel P state, specifically for those platforms we have today with the interaction firmware kernel we have today, of letting Intel P state override what menu.
Because Intel P state doesn't know two things. First, it doesn't know that there is a power budget, and second, it doesn't know that that using a specific idle state is needed to unlock some power needed to, because you don't know how much power is needed to run at the specific P state in Intel P state. It is like the firmware knows that, but the driver doesn't, and those power numbers are never available anyway.
But this is like platform decided, so we could teach Intel P state that information. Actually, we don't necessarily need a new firmware for that. We could.
Yeah. So in Intel P state is actually something like CPPC, right, on ARM, which. So in the CPPC situation, you have basically the firmware decides what P state to use. It's not like you tell it like that you can set limits, but not you don't decide what frequency to run.
You can. In the ARM implementation, you can do both. You can do an autonomous mode and a non-autonomous.
Yeah, I know about that. I'm talking about autonomous.
But we still have a reasonable estimation in the kernel if if the other CPUs are super busy, then it's very likely that a higher P state would be used if the power budget allows, right? Like, we are not completely oblivious to the fact.
Yeah, so right. Anyway, so that's something to discuss going forward, right? And so this is not like a something we can address right now, or even today, or even at this conference, but something that we need to think about, like how to take all that into account again, in my view.
For me.
Yeah, that's all.
Okay.
Thank you.
Is this only just Berlin, or what platforms like would like this problem specifically? Is this likely only Jasper Lake? Is that like a one?
Hopefully yes, but the power budget existence, I would say, is
of course,
is it's a fact of life, and it will be there going forward, because the systems are, more more and more powerful, and more thermally constrained, and more power constrained. If so, if you want to run a PC in a handheld case, basically that's a challenge.
I would be very curious because the power budget works in like windows, right? Like it takes these like window, like how much power was used that window and that window. That's how it determines if you're still in the power budget. And presumably what happened on Jasper Lake is that we burn, like let's say this is our window, burn much more power here and maybe much more power here, but because of that wrong idle decision, our current window was relatively like underutilized, and therefore these were unlocked. So maybe, I don't know, can we play with those it's a firmware thing, but
yeah, we can. Still, this is something that needs to be kind of researched and discussed, right? But again, this is something that we really haven't taken into account, all those power budgets and then power distribution and things like that. We haven't taken into account that much so far. And apparently it's something that, it would be good to consider as well. All right, thank you very much. There is a list of references in the slides, so hopefully clickable. I'm not sure if they are still all active actually, but yeah, please try if you're interested in that. And there is a sponsored disclaimer.
We have a question.
How is the future idle time estimated?
It is based on the idle times from previous iterations. So the statistics are collected essentially.
We also look at timer, like we know the next.
And a timer, yeah. So
the menu doesn't look at the timer, right?
Does.
Yeah. Is it based on the CPU, or is it based on the thread?
It's based on the CPU, yes, on the current CPU.
So if a new thread has arrived on CPU that has totally different.
Yeah, if there is a change in behavior, then we will not. We'll need some time until it becomes like visible.
Yeah, I'm going to ask a question probably many people don't like. What's your opinion on going towards like a SCADX direction, where there's user-defined information passed into CPU idle? Because what we found is like on phone, simply knowing whether the screen is on or off can significantly improve the CPU idle decision.
So I told somebody that, okay, I have nothing against parameterizing CPU idle governors, but I don't see why we have to go all the way to parameterizing it by code, which is BPF essentially, right? Because BPF is like arbitrary parameterization. You just allow people to change the behavior essentially. But parameterizing is fine, but why to do it?
When I will talk on SCADX about this, but what I found is like there is some overhead also in the coding into BPF, right? And actually in CPU idle, the wake up, we are super sensitive. The code we execute at wake up when exiting, do it super sensitive to.
Not only that, but I honestly haven't seen any examples of cpuidle governor parameterization that improve things. Any, not just by allowing a BPF program to run in the governor context, just any kind of.
So yeah, I'm not going that far as like running BPF, just passing some user-defined bits over. Right?
Yeah, parameterizing is fine. If you can, find a parameterization to work for you, yeah, good for you.
I think we already have one. This CPU QoS latency idle.
Yeah, so there is QoS, but it's indirect. I mean, I'm talking about the direct parameterization, like having a tunable SysFS or something for an idle governor. If somebody can come up with something that will improve things, all power to you. But I haven't seen one.
We have one option in Teo is we would have one. We do like some statistics, and you could parameterize this like threshold quite easily. I think the patch would be very easy, but someone would have to do have to prove the benefit.
Yeah, so